Excuse me. Okay, so in this video, I'm going to continue to go over section 5.8, moment generating function. So 5.8, all right, so so moment generating functions is the what moment generating function is expected value of exponential e to the tx, right? So if we're doing that, so we learn the earth moment about the origin. So we learned it, right? So mu, first one, mu r prime. That was the earth moment about the origin. Give me a second. So now that was the expected value. Was expected value of x to the r's power, right? And then that was the sigma, the x, and the x to the r's power, and then f of x. Here, f of x is the probability distribution function of random variable x. Okay, and if x is a discrete, the e to the x to the r's power is equal to this. And then if x is continuous, then expected value of x to the r's power is going to be integral of x to the r's power times f of x dx. Okay, so negative infinity infinity, right? So now, and then the moment generating function was denoted by mx, right? T. That was the expected value of e to the tx. Okay, so its definition is this is defined by sigma e to the tx. By the way, this is r. Okay, e to the tx and the f of x, x and the integral negative infinity infinity e to the tx and the f of x dx, right? And then we learned the relationship between the earth moment about origin and then moment generating function. So mu r prime was the r's derivative of moment generating function, right? So that was the mx t over the t to the r's power. Okay, and the t equals 0. Okay, so using that relationship, we could figure out the mean and variance of the binomial distribution, right? That was example 5.30. So, and then from there, what expected value of e of x, which is mu, that was equal to mu 1 prime, and the sigma square was the what? Mu 2 prime minus the mu 1 prime square. Okay, mind this. Okay. So now we'll see another example with example 5.31. Okay. So example 5.31. So we're gonna find we're gonna determine the moment generating function and then verify mean and variance of the normal distribution. Okay. So this is moment generating. For a normal random variable. Okay. So excuse me. So suppose that x has normal distribution. Okay, so x is a random random variable of normal distribution. So then f of x is gonna be 1 over sigma square root 2 pi. Okay, and the e to the minus x minus mu square divided by 2 times sigma square, right? So first one, we're gonna determine the moment generating function. Okay, so moment generating function, that's going to be since the here in this problem x is a continuous random variable, So we know this is, keep in mind, this is e to the tx, right? Okay, tx. So which is, since x is continuous random variable, we have to evaluate integral negative infinity to infinity, the e to the tx, and then f of x, which is a PDF of the normal random variable. That's this, right? So we plug in this one into here. Wait a second. Okay, so that's going to be f of x, right? Which is 1 over, sorry, sigma square root 2 pi. Give me a second. So 1 over sigma square root 2 pi times e to the minus x minus mu square over 2 sigma square, right? The dx. Right. So let's evaluate that in definite order. So that is equal to first one. I want to combine that exponential with this exponential. Okay. So combining these two guys, then we're gonna get this. Let me take out 1 over sigma square 2 pi out of the integral. Okay. So 1 over sigma square 2 pi, and then integral negative infinity to infinity, and then e to d, right, minus the x square minus, because I'll see x minus mu square is extending this one. I mean, I'll just doing the FOIL, this perfect square term, we're gonna get x squared and then minus, right, 2 times mu x, right? But second, but when you combine these two exponential terms, we have to rewrite t times x as a fraction form whose denominator is 2 times sigma squared. So tx is actually 2 times sigma squared tx over 2 times sigma squared, isn't it? Okay, you see that 2 times sigma squared tx, this is kind of x term, right? We can say that. All right, so we're gonna combine this guy with minus 2 mu x. Okay, then we're gonna get minus 2 times mu plus t times sigma square and the x. Okay, and then plus mu square. Right? And then divided by 2 times sigma square. Okay, and then dx. Okay, so all right, now then that is equal to, this is equal to okay, so give me a second. So we're gonna get the completing square. We're gonna do completing square from here to get the perfect square form. Okay. So to do that, so now right there. So x squared minus, just take a look at this. X squared minus 2 times mu plus t times sigma square times x, the plus mu square. Okay, so I'll just take a look at numerator of the exponent of that exponential. That is equal to first one. You see, I want to get the perfect square form of for that terms. So first one, let me write down x minus mu plus t times sigma square, the square. Okay, all right. Then we're gonna get what? Then we're gonna get x squared and then negative 2 times mu plus t sigma square, right? And then what? Plus mu plus t times sigma square and square, right? Okay, so we have to subtract the what? Mu plus t times sigma square and square, and then plus mu square, isn't it? Okay. But actually what? So we're gonna get the mu square here, minus mu square plus mu square. So mu square gonna be cancel them out, is it? So now this is equal to x minus mu. See here? So we'll get the, look at this. If you do FOIL right there, we're gonna get x squared. Yeah, so we got we have x squared on the left hand side, right? And then minus 2 times x times mu plus t sigma squared, which is right there in the left hand side. Okay, right? And then we're gonna get the additionally, we're gonna get mu plus t times sigma squared and square. So we have to subtract. Okay, and then we need to add mu squared because your mu squared is in the left hand side, right? But look at this. If you FOIL this one, we're gonna get the minus mu square. So that will be cancelled out with the mu square. So, so we're gonna get the x minus mu plus t times sigma square, the square, okay, the minus, okay, mu square, and then minus 2 t and the sigma square and then mu, and then plus t square sigma to the fourth power plus mu square. So cancel them out. Okay. All right. So keep in mind this. Now then, oh, right here, back to here. So this one, let me, so that integral can be simplified as like this. 1 over sigma square 2 pi, okay? And then e to d integral e to d, so minus, right? X, I'll plug in this one into here, okay? Because we rewrite this one as perfect square form here. Okay, so e to the minus, then curly bracket, and then open curly bracket, and then x minus mu plus t times sigma square and square, okay, and then plus minus this one, right? Minus this one plus this one, minus 2t sigma square mu plus t square sigma to the fourth power, right? Okay, close curly bracket over 2 sigma square and the dx. Now look at this. This is integral with respect to x, right? So e to the minus 2t sigma square plus mu plus t square sigma to the fourth power over 2 sigma square can be what? Factored out. Because e to the this one plus this over 2 sigma square is what? Constant. In view of the integral with respect to x, right? Okay. So I'll take that out. So then we'll get this. 1 over, by the way, 1 over, let me write down that exponential, okay? E to the, this one over 2 sigma square. Give me a second. So right here, excuse me. Right here, I'll take out e to d, this term, okay? Okay. So now then we're gonna get e to d, okay, 2t sigma square mu plus t square sigma to the fourth power over 2 sigma square, okay? Right, and the integral negative infinity to infinity. Now let me put the constant term 1 over sigma square root 2 pi inside the parenthesis, inside the integral, okay? Right. And then e to d minus, and then also what's the leftover in that exponent? Minus this one square over 2 sigma square, right? But we can write down like this, minus 1/2 times x minus mu plus t sigma square, and then square over sigma square and dx. Okay, right here. And then let me simplify this fraction. Then we're gonna get this. Okay, so e to d. Okay, so because these two guys have common factor. I mean, this sigma square, right? So sigma square, sigma square, sigma square, cancel them out. So we're gonna get the two, and also two cancel them out, right? So we're gonna get e to the mu t, right? And then plus sigma square, and then t square divided by 2, right? And the integral negative infinity to infinity, the 1 over sigma square root of 2 pi, okay? And the e to d, yeah, right here. So give me a second. Yeah, so let me just copy it. Okay, negative 1/2. Okay, and then x minus mu plus t sigma square, and the square over sigma square and the dx, right? So now let me use the u substitution, okay, to change a variable. So okay, so let me just copy this one right here, okay, and then times. So here, let's say u is equal to x minus mu plus t sigma square over sigma square. Okay, let me do that. Why? Because look at the integral. This is a similar that one. The form of this one is similar to the integral of the uh, in the what the PDF of standard normal probability distribution. Okay, so I think we can change the form to match the PDF in the standard normal distribution. So let me try. Then once you do this, the sigma square just sigma, okay? All right. Then what du is going to be? Du going to be what? This is going to be just 1 over sigma, right? And then dx. Okay. So, and then if you x approach negative infinity, then u approach negative infinity. If x approach infinity, u approach infinity. So lower limit, upper limit still negative infinity, infinity. Okay. So in the 1 over sigma square root 2 pi e to the negative what? You're going to get u square over 2, right? Is it? Okay. Square. And then dx becomes what? Sigma du, right? So sigma cancel them out. So we got this. E to the ut, I mean, what? E to the what? Ut plus sigma square t square over 2 times negative infinity to infinity, the 1 over square root 2 pi e to the minus u square over 2 and then du. That's the exactly same as what the PDF of standard normal distribution. Okay, and then I mean, sorry, this is the exact same as a PDF. This is the PDF of standard normal distribution. Okay. So now, then what? The integral of PDF from negative infinity must be 1. Okay, so that is equal to 1. So we got this. This is equal to what? E to the mu t plus sigma square t square over 2. Okay, that's the moment generated function of normal distribution. Okay, so now once we figure out the moment generated function of the normal distribution, then we're going to find out the first and second derivative of the moment generated function and replace t with 0. I mean, plug in 0 into d to find out mu1 prime and then mu2 prime. Okay, so now so we got this mx of t is equal to e to d mu t plus, plus right here, sorry, sigma square and then t square over 2, right? Okay, now then mu1 prime is equal to dmx t over dt, right? The t equals 0, right? So that's going to be, so let's take a derivative of this guy with respect x, t. Then we're going to get mu plus sigma square t, and then e to d mu t plus sigma square and t square over 2, and then t equals 0. Okay, now then this is equal to, now we plug in 0 into t, what happened? This term just going to be 0, and then this going to be 0, right? So we got mu times, and mu t is going to be 0. So we got mu times e to the 0, which is 1, mu. Okay, so mu1 prime, which is the first moment about the origin, is equal to mu. Turns out to be mu. Okay. Now mu2 prime is going to be second derivative of the moment general function. Okay. So now this is equal to, then we what? So give me a second. Yeah, so now mu1 prime, yeah, so we're gonna take a derivative of this one with respect t once again. Okay, because this is the first derivative of the mx. So we take a derivative of mx one more time. That's gonna be second derivative, right? So now we consider this one, give me a second. So we say that this is a function, and this is another function. So we apply the Proctor rule. Okay, then we're gonna get sigma square, the e to d mu t plus sigma square t square over 2, right? And then plus mu plus sigma square t times derivative of this one is what? Mu plus sigma square t. So we're gonna get sigma mu plus sigma square t square and then e to d mu t plus sigma square t square over 2, and then t equals 0. Okay. All right. So we plug in 0 into t, so this is gonna be 1, right? Okay. This is gonna be 0, and this is gonna be 1, right? So that is equal to sigma square plus mu square. Okay. Now then what? So expected value, this is what? Mu1 prime, right? So this is mu. Okay, we verified that. And the sigma square is equal to mu2 prime minus mu1 prime square, right? So that is equal to, we just get mu2 prime, right? Which is a sigma square plus mu square, right? The minus mu square, which is a sigma square. So we verified that. So, okay. So we got sigma square, right? So what does that mean? So this one verified that what? This one can tell us that what we can find out the expected value and variance by using the moment general function. Okay, so here we already know that what expected value and the variance is mu and sigma square in the normal distribution, right? So we just verified that. Okay, now next one is the we'll see the properties of moment general functions. Okay, so okay, the first one is the uniqueness. The moment general function of random variable is unique when it exists. Okay, keep in mind this moment general function is unique. So the next one, yeah, let me just show the my lecture note. Yeah, so can you see that? All right, so here uniqueness, keep in mind this, and then next one. And then if we have, it means that with this, if we have two random variables x and y with mx, my, and mx and my are two momentary functions equivalent for any t, then x and y have the same probability distribution. For example, if x is a normal distribution, y is a normal distribution with the same the momentary functions, then two probability distributions, normal distributions, they're the two random variables x and y should have the same probably normal distribution. Okay, so now next one, properties of momentary functions. Mx plus a is any real number. Okay, so there is e to the at times momentary function of x. Okay, so here's a proof. It's not that hard, right? So we just use definition of the momentary functions. Definition of momentary generating function is expected value of exponential term e to the t times, in this case, x plus a, right? But so well, exponential term satisfy linearity, so we can take out e to the a times t. And now expected value or just satisfy linearity, we can take out e to the a times t. So we got this. Okay. So right here. Let's say. So, but e to the tx, expected value of e to tx is, this is the what? That's the moment general function of x, right? Okay. So now next one, m the what? M times max is equal to moment m sub x of a times t. So also, yeah, this one can be proved easily just using the definition of the moment general function. So m sub ax, this is expected value of e to the t times ax. Okay, so then then what? We can, using associate property, so we can say that e to the at times x. So that's going to be, so we can say this is a more general function, m sub x of a times t. Okay. So now next one is important. So if x1 through xn are independent random variables with the moment general functions mx1 through the mxn respectively. Keep in mind this. Here we assume that x1 through xn, these random variables are independent, okay? And their moment general function is mx1 through mxn. Now, you see, if y is new random variable y is defined by the linear combination, but simply just sum of x1 to xn. Okay, then the moment general function of y is the product of the moment general function of x1 to xn. The pi, capital letter pi, means the product. Okay, okay, similar to the sigma, but not just sum of mxi, but product of mxi. Okay, so let me prove this. So right here. So let's prove this. My is defined as sigma, okay, I goes 1 through the n and xi, okay? And then my t, that is equal to pi, I goes 1 through the n, mxi of t. Okay, so here's a proof. Okay, let me prove it, and then let's just call it a day, okay? So consider, we just, without lose a loss of generosity, let's say x1 to xn are continuous random variables. Okay, so then my of t, that's going to be expected value of e to the ty, right? So that is equal to expected value of what? E to the t times, right? And the sigma I equals 1 through the n and xi, right? Okay, so now that is equal to, so since we assume that x1 to xn are continuous random variables, this is going to be what? Integral, right? Negative infinity to infinity. But we learned that in 5.6 linear functions of random variables. So that is equal to what? the multiple integrals, right? The e to the t times sigma I goes 1 through the n xi, and then f of x1 through the xn. This is the PDF. Okay, PDF of the what? PDF of the x1 through xn. Remember, okay, so dx1 through to dxn. Okay, so we need to figure out this one, right? So what is this? So now keep in mind this x1 through xn are independent. Then we learned in 5.6 linear functions of random variable. If x1 is a multiple variable, x1 through xn are independent, then that is equal to actually the product of random variables, a product of the PDF for each random variable xi, okay? I goes 1 through the n, okay? So what that means, this is the what? fx1 times x1 times fx2 times x2, okay, through the fxn of xn, okay? So now then, so that is equal to, can you see that? Okay, so now this is equal to, yeah, we need to figure out this one. But since x1 through xn are independent, so by the property of linear functions of random variable, which we learned in 5.6, that is equal to product of the each what the PDF of xi. Okay. Now then, so plug in this. Okay. Since the what integral also satisfy linearity, so that's going to be the multiple integral of this one is equal to a product of the multiple integrals. So now this that is equal to negative infinity to infinity e to the t times x1 times fx1 and of x1 dx plus, because this parcel that is equal to what? E to the t times x1, it should be lowercase x, right? Lowercase x1 times e to the t times x2 times through the e to the t times xn, right? Okay, so plus the negative dx1, negative infinity to infinity, and not plus multiplication, okay? Multiplication, the e to the t times x2 times fx2, okay, and then x2 and then dx2 times through the negative infinity to infinity e to the t times xn, fxn, and the xn, and the dxn. Okay, so now then what? So each one is what? Each one is the moment generated function of x1, x2, x3 through the xn, right? This is moment generated function of xn. This is moment generated function of xn. So that is equal to pi moment generated function of x I 1 through the n. Okay, I prove it. Okay, all right. So next one. Now next one. Let's see example. Okay, 5.32. Okay, in textbook. Yeah. So let me. Yeah. So let me stop here. All right. So I think I covered enough. So please review especially how to find the moment generated functions and then how to determine the mean and variance using the moment generated function. Please review the examples in the textbook. Okay. So now we're gonna look at example 5.32 next time. Okay. All right. That's it.